A water tank is open to the atmosphere and filled to a height of 3 meters. Okay, so this here is 3.0 meters. The tank is punctured as shown, and a stream of water lands on the ground at a distance of 1.0 meters from the side of the tank. And we're asked to find the vertical distance from the hole to the top surface of the fluid. So using some simple kinematics, we have the horizontal distance of 1 meter is equal to the initial speed. So that will be v2. If I take this as 0.2 and take this as 0.1 here. Okay, so the distance is going to be speed by time. Now using Torricelli's law, we know that v2 is equal to root 2 gh. Okay, so this is by Torricelli's law, where we assumed non-viscous steady state flow of an incompressible fluid. So in this case we have water. Now if we take our kinematic equation in a vertical direction, and I'm going to take this as my reference point, y equals 0 here, well, what we have is the fluid in freefall. So the only acceleration acting on this fluid is gravity. So what we do is use this kinematic equation. So y is equal to y naught plus the vertical component of velocity by time, and then plus the gravitational acceleration by time squared on 2. So in this case, the speed of the flow is purely horizontal. So effectively this term here is 0. And my initial point of the motion is y equals 0. So y naught is 0 here. And we can see that the final y position of this stream is this distance over here. So that would be the depth of the water minus h. Okay, so we can write this equation as 3 minus h, and that's equal to gt squared on 2. And now if we substitute for the speed into here, well, what we get is 1.0 is equal to root 2 gh by t. And if we square both sides of the equation and divide through by this term, what we get is 1.0 over 2 gh is equal to t squared. And now we can substitute for t squared into this equation. So what we get is 3.0 minus h is equal to g on 2 multiplied by 1.0 on 2 gh. And we can see we're going to get a cancellation here. And therefore 3.0 minus h is equal to 1 on 4, which is 0.25 on h. And if we multiply through by h, well, what we get is 3h minus h squared is equal to 0.25. And rearranging this equation, so we get h squared on the right hand side minus 3h on the right hand side plus 0.25, and that'll be equal to 0. And now we can use the quadratic formula. So h is equal to minus minus b, which is positive 3.0, plus or minus the square root of b squared, which is 9, minus 4 by a by c. And that's all divided by 2a, which would be 2 by 1. So that's going to give us 3 on 2, which is 1.5. Then plus or minus the square root of 9 minus 1, which is 8, on 2, which is equal to 1.5 plus or minus 2 root 2 on 2, which is root 2. So if we calculate this out, what we're going to get is h is equal to 2.914 or 0.086. And that unit is in meters. And if we look at the significant figures in our problem, we have two significant figures for the height of the fluid and the distance from the tank. So we'll take two significant figures in our result, so that will be h is equal to 2.9 meters, or h is equal to 0.086. So this here is our result. And let's make sense of this. Well, one result is that the hole is going to be 2.9 meters from the top of the tank. Okay, so that makes sense. Well, we also get a second result where the punched hole can be at 0.086 meters from the top of the tank, or 8.6 centimeters. And why do we get two results that give us the same distance? Because this stream of fluid is also going to drop to the same distance from the side of the tank. Well, because over here, the stream of fluid is going to be in free fall for longer. And also, the speed of the fluid here we expect to be smaller. Okay, so when the distance from the punctured hole from the surface of the fluid is smaller, then the exit speed, or the efflux speed, is going to be smaller. Okay, so we get a larger free fall distance and a smaller initial speed. So really have a think about that. And I'll see you in the next video.